Hi, welcome to the first talk of the LD Talk series. In this talk, we will talk about channel capacity from the perspective of data communication and networking. So this is the outline of the talk. We will talk about communications and try to understand it qualitatively. Then we will talk about the basics of the channels, which will help to understand the more finer concepts of noiseless and noisy channels. Then we will talk about the Nyquist capacity and Shannon capacity along with the signal to noise ratio. Then we will make some approximation in the channel capacity and we will exploit the expressions, how the Shannon capacity expression change. And we will on the fly check some numerical examples, and in the last section we will try to deduce the Shannon capacity expression. Okay, so now the question is, what is communication? So there is a several kind of communication we know. If we talk with someone in personality, that is also a kind of communication. If we make some telephonic conversation, that is also kind of communication. And also there is a Wi-Fi connections, and if we transfer some data over the Wi-Fi network, so that is also kind of communication. So now if we say A communicates with B, what does it mean practically? So that means there is a physical act of A which induces some desired physical state in B, as in the picture depicts. So we can see there is a message going to the encoder, and that is encoded bit stream passing into the channel, and with some probability it creates another binary bit stream which feed it into the decoder, and we get some estimate of message. So now the point we have to see, there is a message and there is an estimate of message. So why this is not both of these quantities is not same? Why this is not the message itself? Because during the encoding and the channel there is some amount of loss or something we have to consider. So for the noiseless channel there is no loss, and for the noisy channel some amount of loss which we can bear, but still can fetch the important information out of the channel. So now the question is that when we can say there is if the A and B communicate with each other and the communication is successful. So we can say the entire communication is successful when B and A both are agrees on the same point. For say A sent to the B his or her the geolocation, and B get the same geolocation, and both party agrees on the same point that yes, I have sent this message, and B send a message, yes, I got the same message as you said. So this is a successful communication. So now in the communication there is another questions that every input induce some probability distribution on the output sequence. Since two different input can result a same output sequence, so there is some kind of confusion. So our main motive is to choose such kind of input sequence so that there is a high probability of the output becomes a unique output sequence, so that there will be no confusion. So as this source is widely spread, so and we can transmit it through the channel. So if we consider some real systems, there will be some amount of noise which will create some error into it. So but for that kind of situation we need some kind of error recovery schemes or error correction schemes, so that we can allow some amount of errors or disturbance in the information, but still we can regenerate at the receiver end. Well, now we will go to the basics of the channels. What is the channel, how it works, and so on and so forth. So now the very two basic things we have to understand: what is channel capacity and what is bandwidth. The channel capacity is the maximum rate at which this the data transfer can take place. Okay, the maximum possible data under some given conditions. So that is the channel capacity of any particular channel. So every different channel have the different maximum possible capacity. So what is the bandwidth? So here I have mentioned that the bandwidth is the difference between the higher and the lower, or the maximum and the minimum frequencies. So yes, we can understand this mechanically, but formally if we have to understand it, the range of frequencies where most of the energy is concentrated, because all these signals and everything deals with some analog voltage, so there is some energy. So there is grossly two kind of channels we can discuss. That is noiseless channels and other is noisy channels. So Nyquist capacity, the expression given for the noiseless channels, and the Shannon capacity is for the noisy channels. So what is the noiseless channel? So by the definition of a noiseless channel, that where there is no effect of random influences or the random noise. So that means in case of noiseless channel, we can think that the efficiency is 100%. There is no random error. So whatever I am sending from the sender side and whatever I am getting from the receiver side, both should be same, exactly same. So there is no frame lost or duplication or corruption of the data. So here I have mentioned the Nyquist capacity. So now we have to question the system, how much realistic it is. This is practically unrealistic. Obviously, for the theoretical sanity, we can think about that there is no noise in the channel. But in case of real world system, there obviously some amount of noise are there. That's why we need the error coding schemes so that we can rectify the errors from the output sequence. So here is the Henry Nyquist, who gives the Nyquist capacity. So what is the Nyquist capacity? So there is a assumption channel is free of noise. Okay, so from the sampling theorem we can understand if there is a channel of the bandwidth B, the maximum signal rate could be twice of the bandwidth, not more than that. So if we think the entire signal with m levels, so it can carry log 2m bits. Why the base of the log is 2? Because we are here dealing with binary systems. So what is the trade-offs of this capacity? That if we increase now from this expression, it is quite simple to understand that if we increase the bandwidth, the capacity will increase, so the data rate. And also if we increase the number of levels m, that is also increasing data rate. And there's another thing, that if we increase the signal levels, it's to the receiver to regenerate the message what the sender sent to him. So this entire expression of this Nyquist capacity, it's really silent about the limits or about the errors. If we now there is a question, can we increase the bandwidth or the number of levels as much as possible? That is indefinitely. So it's impossible. If we increase the bandwidth or the number of levels indefinitely, there will be, the system will become more and more erroneous, because there is a interference with the other devices because of this large amount of energy. So the entire efficiency of the system will reduce. So here is the basic structure of a noisy channel, a communication channel in which the effects of random influences cannot be dismissed, unlike the previous one. So here we can see there is an information source from a message is passing to the transmitter, and it becomes a signal, and in the channel there is some noise source. So in this kind of noisy channels, there is some distortion and some noise present. And also when receiver gets this received signal, that contains the important information as well as the noise itself. So the receiver needs some kind of mechanism to rectify the received output and recreate or regenerate the original information for this practical use. So we will use the Shannon capacity for the noisy systems. That's why in the real world systems, the Shannon capacity works fine. So now we will talk about SNR before going to the Shannon capacity, because we have to use this signal to noise ratio to understand how the Shannon capacity works and how the error introduced in the system and so on. So what is SNR? It's just a ratio to the signal power to the noise power. Okay, so as this said, there is a ratio, so it's a unitless quantity. So you can see the expressions from the slide. That is P is the average power. So signal to noise ratio is the signal power to the noise power. So if we check we can think of the SNR as differently. If we take a random signal, so we take the expectation value. So we can take the random noise and we have to do the same. So here E is the expectation value, the mean square value of the quantity. So P, the signal noise, and the signal noise power sorry, the signal power and the noise power. So from this power, if we measure in voltage, that gives us the amplitude. So that's why we write this expression, the amplitude of squares. So here is an important point. What will happen if the SNR go beyond less than the 1? The signal becomes unusable, because if the noise is very powerful, so whatever the sequence the receiver will get, that is have no use. So here there's a few examples we can see. I mean, if we want to express the power in decibel, in the previous slide we can see there's an entire SNR in the just a linear term. This is not a logarithmic terms or so. To measure this, we have to need some amount, so that is decibel we use to measure the SNR, that's called SNR in dB. So in the power expression, so this the equation 4 depicts the power expression for the SNR. So if we write the signal to noise ratio in terms of the signal power and noise power in decibel units, so this is an equation. So as the same, here look, if we want to express the SNR in terms of the amplitudes, because if we measure the signal or noise in volts, then what we can measure? We can measure the amplitude only. So if we replace this expression with the amplitudes, then it becomes a square term which comes down, and it becomes a 20 log 10 A signal in dB and minus of 20 log 10 A noise dB. So this is the equation 7, gives the expression of SNR in terms of amplitude. So now we are going to the discussion for our Shannon capacity. This is Mr. Claude L. Shannon. So in the 1948 paper, so Shannon give the expression of a channel capacity, and there is I mean, he go beyond the naive assumption that the channel has no noise. Shannon considered the Gaussian noise, which is additive white Gaussian noise. So what the Shannon capacity exactly gives us? See, it gives us some theoretical upper bound of the data transmission. So here is one thing: if we increase the signal power, it will overcome the noise. So that doesn't mean that we can increase the signal power indefinitely. No, there is some limit up to which we will increase the power. We will see in the later section when we see how to deduce this expression, then we can understand it in a better way. So obviously there is some limit how much power we can allow. So what is the trade-off of this Shannon capacity? That if we increase the bandwidth of signal power, the data rate will increase. If we increase the noise, the data rate will decrease. If we increase the bandwidth, if we increase the bandwidth, then the data rate will increase obviously, but with the increasing bandwidth we will allow more noise also. So if we confine ourselves with a very small bandwidth, there's a less chance of the effective noise. But if we spread the entire spectrum to a very wide bandwidth, there we will allow the more noise also within that spectrum. So with the increasing of the signal power, more and more noise and errors will be introduced within the system. So here is some numerical example. For say we have a spectrum of 3 megahertz and maximum 5 megahertz. Obviously this is unrealistic because this spectrum is quite widespread, but okay, it will work for this example. So here we have given that the signal to noise ratio is 30 decibel. So the bandwidth is given is 2 megahertz. So if we want to calculate the exact SNR, not in decibel, the ratio amount, that is 1000. So what is the Shannon capacity? We can use this formula straightforwardly and get the Shannon capacity value around 19.934 Mbps. So obviously this channel capacity measured in beats per second, as we consider this frequency in megahertz. So if we put, if you just plug these values in this equation, you can get this also in the 10 to the power cube order. So that's why it's a Mbps. So for the previous numerical example, what we can do if we want to find the how many signal levels we need. So whenever we are talking about signal levels, that obviously incorporates the Nyquist capacity, because there is an expression for signal levels in the Nyquist capacity only. So now, as we have seen that the channel capacity is 19.934 something, so we will consider this channel capacity is the Cn equals to this thing. So from the expression for the Nyquist capacity, we can see that the value of m will be 31 point something, which is to the which if we find the nearest integer of that will be 32. Now the question is why if the value is 31 point something, if we calculate the value exactly will be just a minute, the value will be 2 to the power. The value will be nearly 31 point so on, but for the as the number of levels must be an integer, so we can go to the ceiling of that value. That's why we chose the 32, which is roughly 2 to the power 5. And if you calculate the entire thing, that will be 2 to the power 4.89, something like that. Okay. So now the question is, if we allow 32 levels, how efficient the system will be? In reality, it will be very less accurate. Okay. So if we allow 32 levels for the signal, and whatever the result we will get, that obviously very less accurate. So we will check the few points on Shannon capacity, that what the Shannon capacity actually tells us. The Shannon capacity determines an upper bound on how fast we can communicate over a channel. Okay, so obviously we can see from the expression that the channel capacity is directly proportional with the bandwidth. And also, this is a hard limit that we can't go beyond this bandwidth limit, which is this upper bound controlled by this bandwidth. So now the Shannon capacity gives us a upper bound. So there is no way to exceed it. Whatever we can do, we can try to achieve the maximum possible value as possible. So what is a no transmission condition? If we choose the noise very higher than the signal power, then this entire ratio going to 0 and the log 1 will be 0. So that is the if the system allows so much of bandwidth and so much of noise, then exactly the entire capacity going to be 0. That is quite practical in sense, because if there is a lot of noise, whatever we are getting or whatever we are listening, that makes no sense to us. So now if we increase the S, that will enhance the system performance, but not indefinitely. So we need a cap of this power device. So if we check the we will check a numerical example so that we can understand what is actually happens in the LT devices. Also there is some power rating, whatever the devices we use nowadays, so there is a power rating. So now just a minute. Okay, so in case of when we design the system, for say we keep the channel capacity maybe half, then we can understand that there is a lot of room to enhance the system performance. But if we choose the bandwidth and the signal and noise power ratios, and we get the CN around 9.99 or something, so we can understand that okay, we are getting some good design which will work at best. So here I will expect to pause the lecture and understand whatever I have gone so far. Okay, so now we are taking some real example. So in a daily life situation, we see a lot of LG operators which run some advertisement of giving us so much of hundreds and thousands of Mbps download speed, but in reality we get maybe 1/10 of or less than that. So then what is the true capacity of this channel? For say the maximum bandwidth for a LTE channel is 20 megahertz. So now I assume there is a 4 different signal to noise ratios with equal probability, that's 3, 6, 9 and 12. So if we use a Shannon capacity, then we can find that for the each of the this SNR ratios, we get the C1 to C4 amount of channel capacities. And if we take the average of that, that will give us roughly around the 55.67 Mbps. So that is the exact true capacity we are getting so far. Okay, so if we change the probability of each of the SNRs, then the values will change accordingly, and it will multiply with some probabilistic factor, and these values will change a little bit, and on the average value will change a bit. But in the running average, we take each of the states will 25% probable. Okay. So there is some approximations in the Shannon capacity formula, that what will happen if we take the signal to noise ratio very large, or take the signal to noise ratio very less. Okay, so if we take it, the SNR is much greater than 1, then we will call the region, whatever the region we call, I mean that is called the bandwidth limited region. So you can see very evidently, if we say this is SN1 is very larger than 1, it roughly becomes the log of S by N. So if we change the base, I mean we can always do the log 10 by log 2, and log 2 by log 10 and log 10 of S by N. So the log 10 by log 2 becomes 3.32. And if we change this entire expression into the decibel SNR TB, so this becomes a 0.332 SNR TB. And if we plug this entire expression into the Shannon capacity expression, then here this is the expression we are getting so far. So here is the thing, that capacity is logarithmic here in power, and is approximately linear. This is called the bandwidth limited region. And for the power limited region, if we take this SNR, the ratio of signal to noise is very less than 1, then we have to change the base into E. And if we change all this algebraic things, then we will get the result of 1.44 times of the SNR. So if we plug this value into the Shannon capacity formula, we will get this is the this is SNR times bandwidth times 1.44 is the Shannon capacity. So this is the power limited region. So in this low SNR approximation, if we allow the white noise, whatever you can remind that we have only allowed the Gaussian noise. So if we allow the white noise, consider there's a spectral density of n0 watts per hertz, then the total noise will be given by, that's a bandwidth times the spectral density, and that will give the total power. So now if we plug this n into the expression, you can see this bandwidth in the denominator and numerator will cancel out, and there's a very interesting thing. The entire channel capacity is independent of the bandwidth. So that's very nice feature we are getting here. So if we plot this result, so this is Shannon HWTN capacity for S by n0, it's taken as 1. So this is the blue line, which is infinite bandwidth limit. And if we check the capacity with the power limited and bandwidth regime, so you can get this is a linear region here, and there is a linear region here. So I guess up to this point, that's quite clear. So I will take a pause here. If you want to go back and understand things, that will be okay. So okay, I guess now we can move on to the next part. So we have completed all the sections. So we have come to the last end of this entire talk, that we have seen the Nyquist capacity and the Shannon capacity, but we can't prove this capacity formula, that is beyond our scope. But obviously we can try that to deduce the expression to understand what is really happening. Okay. So now okay, so this is the expression here, the values are mentioned here. Okay. So now the thing is, the signal looks like a noise. What does it mean? I mean, let a signal which is successfully communicated, so we can represent it with some analog voltage levels. Okay, so if we check the analog voltage levels for two different times, that is T1 and T2, we can represent it, and from the sampling theorem we can say the voltage appears at the T1 and T2 are independent from each other, so that they are far enough apart. So if they satisfy this condition, we can think this is worthy to sample independently. So now there is something more we have to understand about the system. The voltage levels are predetermined for each of the data information in the sender side. The voltage levels are predetermined, but the receiver have no idea until he or she receive the receive the output from the decoder. So now if I ask a question, what if the receiver have the preconceived idea or some predetermined idea what of the voltage? Now if the receiver have the idea of the voltage, whatever the data he or she going to get, then he or she can generate the message in his or her lab independently before getting the data from the sender side. So if this case happens, then there is no sense to send the data itself. So there is no new information the receiver is getting so far. So now as the receiver have no idea about what he or she going to get in the next time instant, so from the receiver perspective, it's varying from time to time. So it's random in nature. So that makes sense. In case of noise also, we have no predetermined idea whatever going to happen. So from the receiver perspective, the signal and the noise both are statistically same, both are not predetermined, both are random in sense. So now the question is how to reduce this randomness, because in the receiver side one have a signal, and also he or she has the noise itself, but we have to do some thing within the signal so that we can distinguish the signal from the noise itself. So we can add the parity bits, which obviously introduce some amount of redundancy, and this redundancy obviously reduces the efficiency, but it helps the receiver to distinguish between signal and noise. Okay, so the amount of noise the system can be expressed in mean noise power. So Vn is the voltage of the noise, so the power is the Vn square by R, and the signal power, average signal power, is the Vs square by R. So this R is the characteristic impedance of the system, and the voltage Vn and Vs is the RMS values. So now as we discussed before, this noise and signal we have seen in the Nyquist theorem and the Shannon capacity itself, that if we increase the bandwidth, then the capacity will increase. If we increase the signal power, it will increase. But what is the practical upper bound? I mean, how much this voltage can go up? There must have some scaling factor or form factor which will just limit this increasing voltage. It can't go indefinitely, because if we allow this voltage to increase indefinitely, it will create some interference with the other devices, and obviously the entire efficiency of the system will reduce, and it makes no sense of a system, and obviously this is not a good design itself. So, and for the noise term, we can say this is the, if we allow the noise from the negative side to the positive side, so we have scaled with the gamma factor, this Vn, and for the noise we always try to reach as much as possible. That's why we express the gamma with the Vs max, the maximum allowable voltage, and the Vs is the RMS signal voltage. So what is the total power? So total power, obviously the signal power and the noise power, and if we try to calculate the RMS voltage of the entire thing, then the equation 14 depicts that. So now the question is, as we chose, I mean, as the signal and noise are statistically both similar, so we take the same form factor to scale both of the parameters. Since S and N having the same factor, so Vt will be confined. So now the question is, I mean, what is the range of Vt can move? Okay, so as the constituent factors of the Vt is bounded by the S and E separately, so, and the both of the terms are scaled by the same form factor gamma, so Vt max also confined or scaled by the same form factor. So now we have the entire range. Now if we want to divide the entire range into some sizes, for say we range into 2 to the power b band of sizes delta v. So if we want to distribute the entire or sample the entire range in 2 to the power b bands, then we need at least 2 to the power b numbers to label the each of the bands separately. So, and so for this purpose we can consider b bit of binary numbers for each of the delta v sections. Okay, so what practically we are doing, whenever we are getting an entire spectrum and sampling it with some 2 to the power b numbers and taking some b bit binary numbers to label the each of the delta v sections, practically we are doing some analog to digital conversion over the entire 2 Vt range. Okay, so now the question is, I mean, what will be the value of the b? So we can use a b-bit binary number to indicate each of the delta v at any of the moment. Okay, so there is no point of choosing a b which violates the condition. I mean, if we choose some such of b for that the delta v is less than the twice gamma vn, then we will allows the, I mean, it will simply tend to noise, I mean, allow the noise and just randomize the entire signal this amount and making the entire system meaningless. I mean, it will introduce much amount of noise and the entire output makes no sense itself. So for a meaningful purpose, we have to choose 2b in the ratio of like this. There's a maximum number of given this thing, and there's some algebra we have done, and we can get the expression of b, which is practically log 2 of 1 plus SNR to the power half. And if we take some make b if we take some b-bit measurements m number of times over a t time, then the total number of bits of the information whatever we have collected so far, that will be m times b, and we can plug the expression for b in the same equation. And what is the information transmission rate? As we have done this entire h in the t time, so h by t will give the expression for this, so which is nothing but the equation 21. So from the sampling theorem, so for a channel with bandwidth b, the maximum sampling rate could be twice of b. So now the maximum information transmission from the equation 21, if we go back to the equation 21, this is the information transmission rate. Now this m by t is the sampling rate, so if we use the highest sampling rate, that obviously gives us the maximum information transmission rate, which is nothing but the channel capacity. If we remember the definition of the channel capacity, that would give the maximum or the upper bound of the transmission rate. So that gives us the Shannon capacity of the channel, which is this is the expression, and if we simplify this, and this is nothing but the Shannon capacity expression. So you have to remember, this is not a proof, but we just want to deduce the expression from considering the signal voltage and the power voltage, and we want to justify the equation so that we can understand what's happening here. So hope up to this point it's clear, and thank you for attending these lectures. All the images are taken from the Google Images, and so if you have any questions, you can comment in the YouTube comment section or the Google Classroom, and if something important I have missed and something, I will comment down below, and I will give the prerequisites links in the card and description boxes. So thank you.